Chapter 3, Instrument Transformers. Instrument transformers. Instrument transformers are a special type of transformer used for the measurement of voltage and current. As the name suggests, these transformers are used in conjunction with the relative instruments such as ammeters, voltmeters, wattmeters, and energy meters, as well as protective relays. Such transformers are of two types. Current transformers. Current transformers are used when the magnitude of AC current exceeds the safe value of the current required for the measuring instruments. Potential transformers or voltage transformers are used where the voltage of the AC circuit exceeds 750 volts and it is not possible to provide adequate insulation on measuring instruments for voltage more than this. These are examples of current transformers that may be found on the bushings of a circuit breaker or a transformer. They are known as donut CTs for their similar look to a donut. The picture on the right is not a CT, but a typical transformer or breaker bushing, which would be mounted through the center of a donut CT. The secondary winding is wrapped concentrically around a toroid, which is usually made up of laminated iron or steel. The primary is a single conductor, usually a bushing, mounted through the center of the toroid. The donut fits over a conductor, bushing, or bus bar, which constitutes the primary having one primary turn. The secondary is wound around a toroid core, which is usually made up of laminated iron that concentrates the magnetic flux and forces it through all of the secondary turns. Some donut CTs come with the primary conductor incorporated in the CT itself, and connections are made by bolting to the primary lead. If the toroid is wound with 240 secondary turns, then the ratio of the CT is 240 to 1, or 1200 to 5. The 5 amps designates the continuous rating of the secondary winding and is normally 5 amps in North America. And sometimes it's 1 amp or 0.5 amps in other parts of the world. This type of CT, or donut CT, is mostly found in circuit breakers and transformer bushings. The CT fits into the bushing turret, and the bushing fits through the center of the donut. It's not uncommon to find up to 4 CTs of this type installed around each bushing in a breaker or a transformer. Let's take a closer look at current transformer ratios. In an ideal transformer with a simple load on the secondary and an AC voltage on the primary, the secondary voltage, V subscript S, is determined by the turns ratio such that Vs over Vp is equal to Ns all over Np. The secondary current is determined by the turns ratio such that Ip Np is equal to Is Ns, or this Is is equal to Ip times the ratio Np over Ns. If Np is equal to 1, then the secondary current is equal to the primary current divided by the secondary turns. In a current transformer, the secondary current is determined entirely by the current flowing in the primary system and not by its own secondary load, which is usually referred to as the burden. However, the voltage across the secondary load or burden is very much dependent on the secondary load. Since the current in the secondary is constant if the primary current is constant, then according to Ohm's law, the higher the impedance of the secondary load, the higher the voltage across the load will be. If the secondary load is very high, say open circuited, then the voltage will rise accordingly and could result in a very dangerous condition. This is why the secondaries of a CT should be shorted rather than opened when not in use, and should never be opened during testing procedures. Both the primary and the secondaries of CTs have relatively few turns of heavy wire and thus low impedance. Subsequently, a current is readily induced into the secondary proportional to the primary current. As we have seen, CTs behave according to this mathematical relationship, where the secondary current is given by the primary current times the turns ratio of the CT. If the primary is 1, or it's a bushing or a bus bar going through the donut CT, then the secondary current is equal to the primary current divided by the number of turns of the secondary. There is a unique problem encountered with CTs. In order to magnetize the core of a current transformer, a certain amount of excitation current is required. Part of the current induced from the primary is used to accomplish this. Since the induced current represents the current flowing in the load circuit, the meter's current coil will be influenced proportionally by the load current minus this excitation current. This represents a small loss of load current, and albeit small, does affect the accuracy of the reading of the secondary. Current transformer losses, called errors, vary for different types of transformers and the burden or the load on the secondary. Standards have been established with acceptable error limits that transformers must fall within. Engineers must take this into consideration when designing, relaying, and metering setups. The transformer ratio of a CT is usually designated by stating the primary current versus the secondary current, and the stated secondary current is usually the rated secondary current of the CT. For a given CT where the primary current is 100 amps and the secondary current is 5 amps, the transformer ratio is 100 over 5, or 100 to 5, or 20 to 1. For the same CT, what would happen if the primary was looped back and then fed through the CT one more time? The CT would see 100 times 2, which is equal to 200 amps, if 100 amps was flowing in the primary. The secondary would then read 10 amps. The transformer ratio would equal 100 to 10, or 10 to 1. This, of course, exceeds the rating of the secondary. However, this is only used if the primary current is too low for the meter reading. In other words, the primary is usually well below 100 amps, making the secondary current well within limits. Designating the polarity is very important, and it's done by marking the CT's primary and secondary terminals. This is especially important for the measuring of power flow direction and when CTs are used for directional relaying. There are standards, but they all pretty much mean the same thing. One primary terminal is designated with a marking relative to a secondary terminal marking. The primary and secondaries are marked to indicate which direction current will flow during each half cycle of current. A primary terminal is marked to associate it with a secondary terminal. We say that the primary terminal is spot with respect to the associated secondary terminal marked spot. In the case of a donut CT, where the primary is the conductor running through it, one side of the CT is marked with a spot. In this case, the front is spot. The back is not. The spot marks can be a dot or any similar symbol. The IEEE, the Institute of Electrical and Electronic Engineers, use H1 and X1 in place of the spots. The IEC, or the International Electrotechnical Commission, use P1 and S1. What this indicates is that when the primary current is positive during the sinusoidal half cycle current into the spot, the secondary current will be out of the spot. And what this also indicates is that when the primary current is negative during the sinusoidal half cycle, that is the current out of the polarity spot, the secondary current will be out of the non-polarity spot. For potential transformers, in general, the ratio of the secondary voltage to the primary voltage is governed by the turns ratio of the windings of the transformer. This relationship is not completely exact for the following reasons. The excitation current that is necessary to magnetize the iron core causes a small impedance drop and a phase shift in the primary windings. The load current that is drawn by the burden also causes another small impedance drop. Both of these produce an overall voltage drop in the transformers and introduce errors into the ratio and phase angle. The net result is that the secondary voltage is slightly different than the ratio of the turns for the transformer, and there is also a slight shift in the phase relationship. These two errors are called ratio errors and phase angle errors, and may be represented and taken into consideration by using the equivalent circuit of a real transformer, which is shown here. The reason for these ratio and phase angle errors in a potential transformer have already been discussed in previous chapters under real transformer losses, and the reason for and the theory behind the equivalent circuit of a transformer, which also applies to a potential transformer, has also been explained. Designating the polarity of a PT is very important and done much the same as in the case of a CT. By marking the PT primary and secondary terminals and/or indicating it on the nameplate. Again, this is especially important when PTs are used for relays and revenue meters. As in the case of the CT polarity, the primary and secondary terminals are marked in such a way that when the primary current is positive during the sinusoidal half cycle, that's current into a polarity spot, the secondary current will be out of the polarity spot on the secondary. Or in terms of voltage, since we're dealing with voltage transformers, a voltage rise on the H1 terminal gives a voltage rise on the X1 terminal. Another type of potential transformer that's in common use today is the capacitor voltage transformer, or capacitor coupled transformer, and sometimes designated as a CVT or a CCVT. A capacitor voltage transformer is a transformer used in power systems to step down extra high voltage signals and provide a low voltage signal for metering or relaying operations. In its most basic form, the device consists of three parts: two capacitors, across which the transmission line signal is split, an inductive element to tune the device to the line frequency, and a voltage transformer to isolate and further step down the voltage for the metering or protective relaying device. The tuning of the divider to the line frequency makes the overall division ratio less sensitive to changes in the burden of the connected metering or protective relay devices. The device has at least 4 terminals, as shown here. A terminal for connection to the high voltage signal, a ground terminal, and 2 secondary terminals which connect to the instrumentation or the protective relays. In practice, capacitor C1 is often constructed as a stack of smaller capacitors connected in series. This provides a large voltage drop across C1 and a relatively small voltage drop across C2. As the majority of the voltage drop is in C1, this reduces the required insulation level of the voltage transformer. This makes CVTs more economical than wound voltage transformers under high voltage conditions, such as anything over 100 kV, as the latter one requires more winding and more material. On schematic drawings, CTs with their polarity markings look something like this, representing the concept of an actual CT. On schematic drawings, PTs with their polarity markings look something like this, representing the concept of an actual PT. This is an actual standard drawing using PTs and CTs with their polarity marks and connected to give the right measurement for a kilowatt-hour meter. You can see the CTs are connected on the lines. They are in the bold type line drawing there, and they have spot markings like a little square on the primary as well as the secondary. The potential transformer is in thinner lines there just to the left, and the spot markings are actually X's on the various terminals of the potential transformer. This is another example where a differential relay protection is on a delta to Y transformer. The spot markings of the instrument transformers, the CTs in this case, are very clearly visible, and including the spot markings of the power transformer for which it is protecting. And this ends chapter 3.